The human relationship with cold is ancient. For millennia, civilization sought ways to preserve food beyond its natural lifespan, understanding intuitively that lower temperatures slow decay. Before the modern refrigerator existed, ancient societies developed ingenious natural cooling systems. In Persia, engineers constructed elaborate structures called Yakhchāls, massive subterranean repositories, combined with wind-catching towers called badgers and intricate canal systems called qanats that exploited evaporative cooling, radiative principles to maintain cool storage year-round. These complexes, built centuries before electricity existed, reveal humanity's persistent drive to conquer warmth and preserve the harvest. In temperate climates, communities harvested ice from frozen lakes and rivers during winter months, storing it in insulated underground chambers or packed with sawdust in ice houses, where it remains solid enough to provide cooling through summer. This ice trade, which would eventually span continents and become a global commercial enterprise, dominated food preservation for nearly 2 centuries. Yet ice harvesting had profound limitations. Supply depended entirely on geography and season. Tropical regions and warm climates could not reliably access natural ice. Transportation of harvested ice across oceans incurred massive loss to melting. The labor required was extraordinary. By the 18th century, as populations grew and cities expanded, natural ice supplies proved insufficient for urban demands. The need for a method to create cold artificially became urgent. Philosophers and natural scientists began investigating the mysteries of temperature and heat, laying theoretical groundwork that would eventually transform everyday life. Their discoveries would bridge the gap between ancient empirical cooling methods and the age of mechanical refrigeration, an era that would fundamentally reshape food systems, commerce, diet, human civilization itself. The turning point arrived in 1755 when Scottish professor William Cullen conducted a remarkable experiment. Cullen used a pump to create a partial vacuum over a container of diethyl ether, causing the liquid to boil rapidly. As the ether evaporated under low pressure, it absorbed heat from the surrounding air so intensely that it produced a small amount of ice. This seemingly simple demonstration contained revolutionary insight. By controlling pressure and evaporation, one could extract heat from air and create cold on demand. Cullen's experiment had no immediate practical application. It remained laboratory curiosity, but it opened a conceptual doorway that would occupy inventors for the next century. The principle he demonstrated would eventually become the foundation of every modern refrigerator. His work represented a transition from passive acceptance of nature's cycles to active human intervention in thermal processes. Over the following decades, other scientists built on Cullen's foundation. In 1805, American inventor Oliver Evans described in detail a closed vapor compression refrigeration cycle, a complete theoretical system for producing ice by circulating ether under vacuum. Evans understood that a continuous cycle could operate indefinitely, repeatedly extracting heat and transferring it away. He documented the concept meticulously, yet, like Cullen, never built a working prototype. In 1820, British scientist Michael Faraday conducted groundbreaking experiments demonstrating that certain gases, including ammonia, could be liquefied under high pressure and low temperature. Faraday's work proved that gases possess thermodynamic properties that engineers could exploit for refrigeration. These theoretical breakthroughs accumulated, each contribution removing obstacles, clarifying mechanisms, preparing the conceptual terrain for invention. By the 1830s, the stage was set for someone to transform theory into functional machinery. The first working vapor compression refrigeration system emerged in 1834, built by Jacob Perkins, an American expatriate living in. Perkins constructed a closed-cycle device that could operate continuously, circulating pressurized refrigerant ether in his design through components that heated and cooled the fluid systematically. Unlike Cullen's and Evans's experiments, Perkins's machine actually worked. It demonstrated that mechanical refrigeration was not merely theoretical, but physically achievable. Yet, despite this breakthrough, the invention struggled to gain traction commercially. Engineers and industrialists remained skeptical. The machinery was complex, required skilled maintenance, and offered uncertain returns on investment. Perkins's refrigeration system remained a technical curiosity, celebrated by scientists but ignored by manufacturers. Over the next 2 decades, others attempted similar systems with mixed results. In 1842, American physician John Gorey designed a working prototype based on vapor compression, intending to manufacture ice machines commercially. Gorey envisioned refrigeration serving hospitals, breweries, and food preservation facilities. Yet despite his vision and technical competence, Gorey's commercial venture collapsed. The market simply was not ready. In 1850, Alexander Twining, another American engineer, patented a vapor compression system using ether and took out patents in Britain, yet commercial success eluded him as well. These repeated failures suggested that mechanical refrigeration, however theoretically sound, faced formidable barriers to adoption. The problem was not science, but economics. Existing natural ice supplies, though limited, remained cheaper and more familiar than exotic machinery, requiring constant maintenance and monitoring. The pivotal transformation came through James Harrison, a Scottish engineer and entrepreneur who possessed not only technical skill but commercial acumen. In 1851, Harrison built a mechanical ice-making machine on the banks of the Barwon River at Rocky Point in Geelong, Victoria, Australia. His design used vapor compression principles similar to Perkins's, but Harrison optimized the system for reliability and scaled it for industrial production. In 1854, he launched the first commercially successful ice-making machine. More importantly, Harrison understood that ice production alone would not create a market. He had to expand the application. Starting in the late 1850s, Harrison introduced vapor compression refrigeration systems to breweries and meatpacking houses throughout Australia and Britain. By 1861, approximately a dozen of his systems were operational at major industrial facilities. Harrison demonstrated that refrigeration could serve genuine commercial needs, reducing spoilage and enabling preservation of perishable goods at scale. His success proved the economic case that others had failed to establish. Simultaneously, another refrigeration approach gained attention. In 1859, Edward Toussaint of France developed a gas absorption refrigeration system, a compressorless design powered by heat rather than mechanical compressors. Its innovation used gaseous ammonia dissolved in water, creating what was termed aqua ammonia. This system offered theoretical advantages: fewer moving parts, simpler construction, and potentially quieter operation. When patented in 1860, Toussaint's absorption refrigeration attracted interest as an alternative to vapor compression. Yet despite its elegance, absorption refrigeration would require decades to mature for practical use. The most significant figure to emerge in the 1870s was Karl von Linde, an engineering professor at the Technological University Munich in Germany. In 1876, Linde patented an improved method of liquefying gases, creating the first reliable and efficient compressed ammonia refrigerator. Linde's innovation was not the discovery of a new principle, but rather engineering excellence. He optimized every component, refined every detail, and produced a machine that worked consistently without failure. Linde's achievement transformed the industry fundamentally. His compressed ammonia systems could employ gases such as ammonia, sulfur dioxide, and methyl chloride as refrigerants, substances far more efficient and reliable than ether. In 1895, Linde disclosed the complete refrigeration cycle that bore his name, providing a comprehensive theoretical and practical framework that other engineers could refine and adapt. Linde himself commercialized his designs aggressively, establishing manufacturing facilities across Europe and exporting systems globally. By the 1890s, large-scale industrial refrigeration using Linde-type systems was expanding throughout breweries, ice-making facilities, and meat-packing plants across the industrialized world. The technology had progressed from laboratory curiosity to essential industrial infrastructure. While industrial refrigeration was establishing itself, a more profound transformation was brewing, bringing refrigeration into residential homes. This challenge differed fundamentally from industrial applications. Industrial systems could be large, expensive, complex, and require specialist operators. Home refrigerators had to be compact, affordable, safe enough for families, and simple enough for housewives to operate without technical training. The first practical steps toward home refrigeration began in the early 1900s. In 1894, Hungarian inventor István Röck and the Esslingen Machine Works partnered to manufacture large industrial ammonia refrigerators powered by electric compressors produced by the Ganz Works. At the 1896 Millennium Exhibition, Röck and Esslingen showcased a 6-ton capacity ice-producing plant, signaling that electric-powered refrigeration was technically feasible at scale. In 1906, the first large Hungarian cold store, with a capacity of 3,000 tons, the largest in Europe, opened in Budapest. Manufactured by Röck and Ganz Works, these projects demonstrated electric refrigeration at industrial scale, but residential adoption remained distant. Commercial refrigerator units continued evolving through the early 1900s, using gases such as ammonia and sulfur dioxide. These refrigerants were highly efficient but carried severe drawbacks. Ammonia and sulfur dioxide occasionally leaked from seals and valves, and when they did, they created hazardous conditions inside the home. Sulfur dioxide was corrosive to eyes and could cause vision loss, painful skin burns, and lesions. Methyl formate, used in some systems, was highly flammable, toxic if inhaled or ingested, and harmful to eyes. No family would accept such danger. The barrier to widespread home refrigeration was not technology but safety. Traditional ice boxes, insulated wooden cabinets kept cold by blocks of ice delivered regularly, continued to dominate American and European homes into the early 20th century, not because they were superior, but because they were safer and affordable. The transformation accelerated dramatically in 1913 when Fred W. Wolf of Fort Wayne, Indiana, introduced the first electric refrigerators for domestic use. Wolf's early models, called Domel-Array for domestic electric refrigerator, consisted of a refrigeration unit mounted on top of an existing icebox. Over the next several years, Wolf produced several hundred units, proving that market demand existed. His designs were not elegant, and they retained dependency on ice, but they demonstrated commercial viability. Simultaneously, in 1914, engineer Nathaniel B. Wales of Detroit, Michigan, introduced concepts for practical electric refrigeration that later became the basis for Kelvinator. In 1916, Alfred Mellows invented a self-contained refrigerator with a compressor mounted on the bottom of the cabinet, the first truly integrated home unit. Mellows began commercial production but was acquired by William C. Durant in 1918, who founded the Frigidaire Company to mass-produce refrigerators at scale. In 1918, Kelvinator introduced the first refrigerator with automatic control mechanisms, eliminating the need for manual thermostat adjustment. By 1920, multiple competing manufacturers were developing home refrigerators, though the market remained small due to cost and technical limitations. In 1922, Swedish students Baltzar von Platen and Karl Munters invented the absorption refrigerator while still studying at the Royal Institute of Technology in Stockholm. The absorption design was quieter, required no moving compressors, and could operate on various heat sources. When commercialized by Electrolux, absorption refrigerators found a substantial market, particularly in regions without reliable electricity. However, early electric home refrigerators faced persistent obstacles. In 1922, one advanced model consisted of a wooden cold box, water-cooled compressor, an ice cube tray, and a 0.25 cubic meter compartment priced at $714, far exceeding the cost of a Model T Ford, which sold for approximately $476. The market breakthrough came in 1923 with two pivotal innovations. First, Frigidaire introduced the first self-contained home refrigerator, a complete unit with all mechanical components integrated into a single cabinet, eliminating the need for basement installation and specialist maintenance. The self-contained design represented an engineering triumph. Complex industrial technology was miniaturized, simplified, and made safe enough for residential kitchens. Second, during 1923, Kelvinator achieved approximately 80% market share for electric home refrigerators in the United States, demonstrating that a reliable market existed. Also in 1923, manufacturers began introducing porcelain-covered metal cabinets, transitioning away from wooden construction toward modern material. Ice cube trays proliferated during the 1920s, marking a cultural shift. Freezing transformed from an auxiliary function of industrial ice making to an integral home appliance feature. The first refrigerator to achieve widespread popular adoption was the General Electric monitor top model, introduced in 1927. The public nicknamed it for its resemblance to the gun turret on the USS Monitor, the Civil War ironclad warship. The design was ingenious. The heat-emitting compressor assembly was mounted above the cabinet and enclosed by a decorative ring that transformed a potential eyesore into an aesthetic element. Over 1 million units were produced, making the monitor top the best-selling refrigerator of its era. The Model Top's success reflected convergence of factors: improved design, reduced cost, established manufacturing capacity, and growing consumer affluence. Electrical infrastructure in American cities had expanded sufficiently to support residential refrigerators. Social attitudes shifted as appliances became symbols of modernity, convenience, and family progress. By the early 1930s, electric home refrigerators transitioned from luxury goods to aspiration items for middle-class households. A revolution in refrigerant safety occurred during the 1920s through the introduction of Freon, a brand name for chlorofluorocarbon compounds. Developed as safer alternatives to toxic ammonia and flammable methyl formate, Freon refrigerants were non-toxic, non-flammable, and stable at all operating temperatures. The introduction of Freon dramatically expanded the residential refrigerator market during the 1930s. Manufacturers could advertise with confidence that their units posed no danger from toxic gas leaks, families could embrace refrigerators without fear. The affordability, safety, and reliability converged to trigger explosive adoption. In the United States, refrigerators transitioned from novelties to commonplace appliances in middle and upper-class homes by 1940. The societal transformation accelerated when separate home freezer compartments became common during the 1940s. Previously, freezing had been incidental to home refrigeration. In 1940, manufacturers introduced home freezer compartments significantly larger than those needed merely for ice cube production. Popular terminology of the era referred to these appliances as deep freeze unit. These devices did not enter mass production until after World War II, when manufacturing capacity redirected to consumer goods and suburban housing expanded explosively. The introduction of home freezers fundamentally altered food culture. Frozen foods, which had previously been luxury items available only through commercial ice cream parlors or expensive restaurants, became accessible to ordinary families. Clarence Birdseye's breakthrough in commercial flash freezing technology had created the scientific foundation, but home freezers made frozen foods economically practical for widespread consumption. In 1955, the domestic deep freezer cold enough to allow owners to freeze fresh food themselves rather than purchasing pre-frozen foods when on sale, enabling families to exploit seasonal abundance and store provisions for months. The 1950s and 1960s witnessed continuous refinement of refrigerator technology and design. Automatic defrosting, which had been introduced experimentally earlier, became standard. Automatic ice making eliminated the labor of manual ice tray filling and removal. Color options proliferated. The early 1950s saw refrigerators almost universally white, reflecting both manufacturing simplicity and consumer preference. Between the mid-1950s and the present, manufacturers and designers dramatically expanded color offerings. Pastel colors such as pink and turquoise gained popularity in the late 1950s and early 1960s. Brushed chrome plating, resembling stainless steel, became fashionable. During the late 1960s and early 1970s, earth tone colors dominated, including harvest gold, avocado green, and in the 1980s, black came into vogue. In the late 1990s, stainless steel emerged as the dominant aesthetic.
These color trends reflected broader design philosophies and cultural value. Refrigerators were no longer hidden utility appliances, but visible kitchen centerpieces expressing household identity and aesthetic sensibility. The side-by-side refrigerator-freezer configuration emerged as a dominant design in the 1970s, breaking the traditional over-under arrangement that had prevailed since the 1940s. Side-by-side units offered greater visibility and accessibility, but required wider kit. Water and ice dispensers built into cabinet doors, available from the 1970s onward, enhanced convenience and became status markers for middle-class households. More efficient refrigeration systems developed during the 1970s and 1980s, spurred partly by energy crises but also by environmental concerns. The problem was Freon itself. By the 1980s, scientists discovered that chlorofluorocarbon refrigerants like Freon damaged the ozone layer when released into the atmosphere. Industrial facilities occasionally leaked refrigerants. Older units eventually corroded and vented their contents. The accumulated damage threatened the stratospheric ozone layer that protected Earth from ultraviolet radiation. Governments responded with regulation. In 1994, most nations implemented bans on Freon use in new refrigerators and air conditioning systems. The transition away from chlorofluorocarbons posed a substantial engineering challenge. Scientists and manufacturers had to identify replacement refrigerants that were non-toxic, non-flammable, efficient, and environmentally benign. In 1990, research identified R134A tetrafluoroethane as a promising replacement. While not perfect, it remains a potent greenhouse gas if released. R134a offered significantly lower ozone depletion potential than its predecessors. Since 1990, R134a has become the dominant refrigerant in home and commercial refrigeration systems. Older R12 systems, still found in many pre-1994 appliances, continue operating in homes and businesses, but cannot be recharged legally with the same refrigerant, effectively extending their operating lifespan or accelerating retirement. The 2000s witnessed the emergence of inverter compressor technology, representing perhaps the most significant efficiency advancement since the introduction of Freon. Traditional compressors operated at fixed speeds, either running at full capacity or turned off completely, cycling on and off as needed. This cycling pattern caused energy waste and mechanical wear. Inverter compressors, by contrast, operate at variable speeds adjusted continuously based on cooling demands. When external temperature drops or fewer cold contents require cooling, inverter compressors reduce speed, consuming far less energy while minimizing wear and tear. Most inverter compressors run between 1,200 and 4,500 revolutions per minute, varying fluidly rather than cycling abruptly. LG Electronics played a significant role in advancing inverter technology through the development of linear inverter compressors, which replaced traditional reciprocating mechanisms with permanent magnet pistons suspended between electromagnets. By adjusting electromagnetic poles continuously, linear inverter compressors reduce energy consumption by approximately 32% and noise by approximately 25% compared to conventional compressor design. Energy efficiency standards, introduced initially in the United States during the early 1990s, drove continuous improvement. Current U.S. refrigerators qualified as Energy Star models use approximately 50% less energy than average 1970. The most efficient units made in the United States consume approximately half a kilowatt hour per day, equivalent to 20 watts continuous operation, a remarkable reduction from 1970s refrigerators consuming 3 to 4 kilowatt hours daily. Larger units with expansive freezer compartments and automatic ice makers still consume substantial energy, up to 4 kilowatt hours per day, but represent a minority of the market. The Consortium on Energy Efficiency further differentiates Energy Star models. Tier 1 refrigerators achieve 20 to 24.9% greater efficiency than federal minimum standards. Tier 2 reaches 25 to 29.9% above standards. Tier 3 represents the highest tier, achieving at least 30% above standards. Approximately 82% of Energy Star qualified refrigerators achieve Tier 1 status, with 13% qualifying for Tier 2 and only 5% reaching Tier 3. The refrigerator's impact on global society cannot be overstated. In the United States, an estimated 99.5% of households, refrigerator ownership remains more prevalent in developed Western countries, but has remained relatively low in Eastern Europe, the Middle East, and developing nations despite growing popularity. Throughout Eastern Europe and the Middle East, approximately 80% of the population owns refrigerators. In China, approximately 65% of the population reports refrigerator ownership, with significant regional variation between urban and rural areas. Urban centers exhibit substantially higher refrigeration ownership percentages compared to rural areas, reflecting ongoing global inequality in appliance access and electricity infrastructure. The introduction of mechanical refrigeration fundamentally transformed the ice trade that had dominated the 19th century. Natural ice harvesting, transportation, and sale was an international commerce involving North American ice shipped globally, with smaller operations in Norway and other cold regions. As affordable home and large-scale industrial refrigeration expanded in the 1920s and 1930s, demand for natural ice plummeted. The ice trade gradually shrank to small-scale local services or disappeared entirely from most regions. Families no longer required regular ice deliveries. Ice production was integrated into every kitchen appliance. Refrigeration's effect on human diet and lifestyle proved transformative. The ability to preserve meat, fish, and other highly perishable foods without processing or preservation dramatically improved food quality and safety. Historical food preservation methods, salting, smoking, fermenting, drying, altered flavors and nutritional profiles. Fresh refrigerated food retained original qualities superior to preserved alternatives. This improvement in food quality likely contributed to increased human height and health metrics in populations with reliable refrigeration during the 20th century. Freezers enabled bulk food purchases at reduced unit costs, allowing families to economize on food expenses and maintain dietary variety throughout seasons. Frozen vegetables and fruits became available year-round, previously unimaginable luxury. Ice cream transformed from artisanal luxury, previously obtainable only by traveling to its manufacturing location and consuming immediately, into a commonplace commodity accessible through. Modern refrigerators incorporate sophisticated technology, reflecting decades of incremental improvement. Advanced models include multiple temperature zones optimized for different food types, ultra-cold freezer compartments at -18 degrees Celsius, meat zones at 0 degrees Celsius, cooling zones at 5 degrees Celsius, and crisper zones at 10 degrees Celsius. Computerized control systems manage multiple fans and compressors independently, allowing precise temperature and humidity regulation in each compartment. Sensors detect door openings, internal temperature changes, and external conditions, automatically adjusting compressor speed and fan operation to optimize efficiency. Water filtration and chilling systems provide fresh, cold drinking water on demand. Automatic ice makers produce ice cubes without manual labor. Glass doors permit inspection of contents without opening units, reducing temperature loss and energy. Looking toward the future, refrigeration technology continues evolving toward greater efficiency, sustainability, and connectivity. Internet-connected smart refrigerators can monitor food inventory, provide recipe suggestions based on contents, alert families to expiring items, and automatically reorder groceries. Energy efficiency continues improving through advanced materials, better insulation, and more intelligent compressor controls. Manufacturers are transitioning toward alternative refrigerants with lower greenhouse gas potential. Hydrofluoroolefins and hydrofluoropolyethers show promise. Solar-powered refrigerators are being developed for off-grid applications in developing regions. Absorption refrigeration, the elegant system developed over a century ago, is experiencing renewed interest as a potentially sustainable option for certain applications. The refrigerator represents one of humanity's most consequential technological achievements, invisible in its familiarity, yet profoundly reshaping every aspect of food systems, commerce, family life, diet, health, and culture. From ancient Persian ice houses through 19th century ice harvesting to 21st century smart appliances, the quest to create cold has driven innovation, investment, and ingenuity. The refrigerator democratized food preservation, making what was once luxury available to ordinary people. It enabled globalization of food markets, allowing produce and proteins to travel vast distances while maintaining freshness. It transformed dietary possibilities, enabling diverse foods to become common. Yet this technological success carries environmental consequences: greenhouse gas emissions, ozone depletion, and electronic waste that future generations must address. The story of refrigeration is ultimately the story of human problem solving, identifying needs, pursuing solutions through scientific inquiry and engineering skill, adapting technologies as unforeseen consequences emerge, and continuing refinement in the endless quest for improvement. The refrigerator in modern kitchens stands as testament to this ongoing human endeavor, humble yet profound in its impact on civilization.